Okay, so we're going to go over some example problems on how to use calculator and how to do different kinds of computation. This problem says, all right, so what's the probability that z is between negative 1.76 and 0.58? So these are different z-scores. So basically, I'm 1.76 standard deviations below the mean, or up to 0.58 standard deviations above. So we write this out. So we see 1.76 is less than z is less than 0.58. So this is, if we think about our normal curve, we've got 1.76, so we've got our mean, and we've got 1.76 below, so we're probably somewhere like here. And we're going all the way up to 0.5 above, so here. So we're looking like this type of area here. It's going to be pretty sizable when it comes to the entire graph. So how do we go ahead and find this exact probability? Well, we're going to do the normal CDF. Our lower bound is going to be negative 1.76. Our upper bound is going to be 0.58. And our mean and standard deviation, because we're using the standard normal, and you know that because we're talking about z-scores, is going to be 0 and 1. Now, this is an unnecessary part. You can just type in negative 1.76 and 0.58, and it'll find it. But again, it's a good habit to get into. So negative 1.76 and 0.58 should get 67.98%. That is our probability that occurs. Or you could type in 0.6798, whatever it is that you choose. But that is what pumps out. So that's the probability that your observation falls within that z-score range. Now, what if they asked me, well, what z-score gives me the smallest 2%? So look at this graph, right? We don't know what the z-score is. We don't know what our lower and upper bound necessarily are. What we know is that we know that we are encapsulating the smallest 2% of that. Now, if we're talking about again, the z-curve. So the z-curve, again, has a mean of 0 and a standard deviation of 1. Well, we can figure out, based off of what we know about the normal distribution, what the z-score is. What z-score has 2% or below as its data. So this is one where we're going to use our inverse norm function. We are going backwards. We know what the area is, right? So the area / probability is 2%, or 0.02. That's the area that's underneath that, to the left. Now this function here is going to tell us what our z-score is that encapsulates an area below it. So it's always left tail, so it always goes all the way to the end. So remember its norm, we start off, we always type in what our area or probability is, and you're going to use 0.02. You got to use the decimal. Now, you should automatically it should automatically choose your mean and standard deviation for you if you're using standard normal. But again, if you want to get into a good habit of typing in your mean and standard deviation, it is not an issue. And so when we go through and use this in our calculator, we should find that this is going to equal negative 2.05 as a z-score. So that's what the z-score is. So 2% of data lies below negative 2.05 z-scores from the mean, or standard deviations from the mean. That's what the inverse norm does, is it takes a probability and converts it to a z-score, as opposed to the normal CDF, which we just used, takes z-scores and converts them to a probability. Okay? Now, what would I have to do? How would I figure out, what if I wanted to just know the z-scores that contain the middle 95%? And this is used quite often when it comes to statistics in the real world. We want to know, with a 95% chance, where should I go? Now, you might say, well, why don't they just do up to 95%? Well, because the range is much smaller if we get closer to the mean, to our mean. So we're going to pick right in the middle, and we're going to go left and right. Okay? So we go to the right and to the left, half of 95%, which is going to be 47.5% each way. So just bringing that up. Now, this is useful to us in that we want to find, we want to find these different z-scores. Now, the nice thing about these two is because we're picking from the left and right of the mean, we can, it's very symmetric, excuse me. And so if we find one, the other is going to be the opposite because they are the same distance away. So you see this question asked quite a lot. Now, one big thing that you want to keep in mind, and the reason why I'm showing you these numbers, is that a lot of people jump to the conclusion when they say, you know, what are the z-scores associated with, you know, the middle 95%? Well, a lot of people see this middle 95% and they think 5%. 5% is the number I need to use. Well, in reality, you're going from the middle of 50%, right? 47% one way, 47% the other, 7.5% the other way. So the actual probabilities that you're using are half of what you think, because you're talking about going from the middle out 95% and not talking about from the beginning. So we can go about this problem in a couple ways. So first off, I think this would be the easiest to find because the inverse norm feature that we have is going to count up to a certain point. So we would do the inverse norm, so the area underneath is going to be 0.025. And if we have a 0 and 1 for our standard deviation and mean, 0.025, we end up with negative 1.96 as a z-score. Now, we can expect the second number here to be a positive 1.96. Now, if you wanted to figure out what this is, to start, we have to think about this a little bit differently, right? We can't just use that area, right? We need that z-score, if we use inverse norm, is associated with this number here, okay? The amount of area that adds up to that, which we can think about like this. This is 95%, and this is 2.5. So we actually end up with 97.5%. So if we type this in, we'll get inverse norm of 0.975 of 0 and 1. And if we do this, we can expect a z-score of 1.96, which is exactly symmetric because we're the same amount of distance either way. It's very critical to understand that the normal distribution is symmetric, but that we have to account for the fact that the middle, left and right, isn't the numbers we have to think about as halving sometimes, right? If we're leaving out 5%, then half of that is down here and half of that is up here. It's very critical to understand. So let's look at a couple actual examples. So if we're talking about There's a paper about fetal growth parameters and birth weight, their relationship to neonatal body composition. So it suggests that the normal distribution has a mean of 3,500 grams and a standard deviation, sorry, I'm switching up the symbols on you, is 600 grams. Is a reasonable model for about birth weight. So they mentioned that it's normal, and that's very key because normally you can't just assume that all the time. It needs to say something that it's approximately normal, that it's close. So now we know we can use the normal distribution. So it says, what proportion of birth weights are between 2,900 and 4,700 grams? So what we need to do is we need to use our normal CDF because we're looking for proportion. Okay, we're looking for a probability, and that's what normal CDF does. So we do normal CDF. Our lower bound is going to be the lowest amount we can allow, which is 2,900. Our upper bound is the largest amount we can have, which is 4,700. Now, this is one where you have to input the mean. So we do 3,500, and we have 600 as our standard deviation. So we go forward here, use our normal CDF, lower bound of 2,900, upper bound of 4,700, mean of 3,500, and standard deviation of 600. And we get that this is 81.86%. And so, obviously, most babies are going to occur between these weights. 81% bet based off of this information, based off that we know what the mean is, we know what the standard deviation is, and we also know what range we're looking for, and that it's normal. It's all key. But that's what this function will do for us. So, anyway. Use this information. The normal CDF and the inverse norm do two different things. So if you had a normal distribution, your normal CDF function is going to tell you the area under. So this is going to equal probability. So that tells you the area under the curve. And your inverse norm that is going to tell you a z-score / value where the probability is a certain amount up to that point. So if we know that 90% of our data lies below a certain amount, that's what this tells us, right? If we know that, that's when we use the inverse norm.